So in this video we are going to look at some of the diode clipping circuits which will clip a part of the incoming waveform based upon if it's more than a certain voltage level or less than a certain voltage level. More important than the circuit itself, we are trying to analyze how to analyze a circuit which contains diode as one of its elements. So in this figure we have a very simple circuit just consisting of a diode, a resistor and a voltage source driven by an input voltage source, and this is giving an output volt, and we are trying to analyze how this output voltage is varying with respect to the input voltage. So to analyze this diode circuit, we are first trying to find out if this diode D shown here is forward biased or is reverse biased. Our analysis can take 2 or 3 steps, and in the first step we are just trying to know what's the behavior of this circuit. And in the first analysis we will assume that this diode here is an ideal diode, which means if it is forward biased it's short, it's connected, and if it's reverse biased it has an infinite resistance or it's open. This is equivalent to an IV curve, where I'll show you the curve in the next figure in a while. So let's analyze this. What happens if this V in is a higher, you can think of that this loop here which has an input voltage and VR here, voltage here, if this V in is much higher than this VR voltage, this end will be at high voltage and this end will be low voltage. So what we do to analyze this kind of circuit is, the first step is to remove the diode from the picture. I have shown it as a dotted thing, which means I have mentally removed it, and this is resistor, this is input voltage V in, and this is output voltage. So I write this condition. If you see this circuit here and mentally imagine this circuit, then if this V in is greater than VR, in that case, if you look at the circuit, this is positive and this is negative. Alright, if V in is greater than VR, this implies D is on. And when D is on, then we can mentally short this thing, this diode here. And if you mentally short this, in that case the voltage V out is going to be the same as V in voltage. Whatever voltage appearing on these terminals is going to appear at the out voltage. So we write V out is equal to V in. And then the second case, when V in is less than VR, which means this voltage is less and this voltage is higher. So this end of the diode is high. So in that case, the diode D is off. And this will be the circuit when this diode D will be off. And in that case, V out will be same as the voltage appearing on this VR, because this is an open circuit. We have not connected any external resistor. So this open circuit voltage here is going to be same as VR. So we write V out is equal to V capital R. So with this information, if I have a plot of the time and input voltage, let's say the input voltage is a sine wave, which I have shown it as a sine graph. And in this sine graph, I have marked a voltage by VR. And this voltage is such that at some point of time, it becomes more than VR. Now we apply these conditions when V in is greater than VR, that means this input voltage, instead of time, this is okay, this is time, but this dotted graph shows the V in. So if V in, input voltage, becomes greater than VR, then we get output voltage. The output voltage I am showing, maybe I should use a different color. So the output voltage I am showing is as this one. The output voltage, which is shown in green, is the same as the input voltage. And when V in is less than VR, in that case, the output voltage stays at VR. So I can draw this output voltage as this, using this line. So this green line is shown as V out, and the black line shows V in. So this is how the output waveform varies with respect to the input voltage. We see that anything less than VR is clipped. So the negative portion of the voltage is clipped. In the same way, if you want to clip, for example, some voltage here, you can reverse this battery polarity of VR, and anything less than, let us say, minus 3 volt will get clipped out. You will only see the positive side, but the negative side clipped out. There are some variations of this circuit. Let's now, in this same circuit, let's reverse the diode polarity. Instead of this way, I make this diode the reverse way. And let's say again, how does this circuit behave? Now, as again, what we will try to do is, let's say what happens when this is the dotted diode. Let's say in the first instance, what happens when V in is greater than V capital R. So if V in is higher and VR is lower, that means this is reversed bias, and in that case I can just mentally remove this diode, and in this case the output voltage appearing here, V out, is going to be same as VR. This diode D is off. In this condition, this diode is off, and we have this condition. In the second case, let's say what happens when V in is less than VR. So when V in is smaller than this VR, then VR is higher, V in is lower. So this diode is forward biased, and in that case we have the circuit like this. And when we have a circuit like this output voltage here is the same as VR. The output voltage is going to be the same as the voltage appearing here, and that can be confusing, because if this is the voltage up here, the same voltage, these two are the copper wires, so that is exactly what's the voltage going to appear here. V out will be equal to V in. And like in the previous example, I can draw a curve which showing the input voltage in green, and then what we are trying to see, what happens if this input voltage is less than or equal to VR. So when V in is greater than VR, then V out is VR. So if it is VR and if it is greater than VR, then V out is clipped at VR. So we have this as this output voltage. I have used just reverse color, my mistake. But anyhow, I will mark it that this green is the input voltage, and we have black as the output voltage. When V in, this is our V in the green, is less than VR, then our output voltage is the same as the input voltage. So this is our clipping circuit which clips the top side of the incoming voltage. So these two are very simple clipping circuit, but there are a couple of variations of this. The one thing that you need to keep in mind is when this, let's say V out is the same as V in, this just follows. And in the other case, when V out is equal to VR, in this case, for example, when the diode is on, I should write diode D is on. In the first case, when the diode is off, like in this case, we get this output voltage same as VR, but you should also keep in mind that there is a resistor, which means that this is true only if you have a load resistance that is much, let's call it R load. If this is valid only if our load resistance is much higher than the R resistor. If the load resistance is comparable to this resistor R, then there will be some drop across this R resistor when the current will flow in this loop. So in order for this circuit to function as a good clipping circuit, we need to keep R as substantially lower than the expected load resistance. So let's move on to some variation of this circuit, in which what we do is we switch the roles of the diode and the resistor, positions of the diode and the resistor. Let's make the resistor R here, and let's put our diode here like this. And again, the same as in the previous sections, let's analyze what happens for the different values of the input voltage. Consider V in is greater than VR. I will say less than, because if V in, I draw the circuit again, make it dotted. V in, VR. If V in is smaller than VR, then this diode is forward biased. When it's forward biased, then D is on. And when D is on, we can just short it and look at the output voltage here. In that case, you can see this output voltage is same as the VR voltage here. So V out is equal to VR voltage. That is our first condition. And the second one, what happens if V in is greater than VR? We have this diode here, and V in is greater, that means this edge of this diode is at higher potential, this edge is at lower potential, this is reversed biased, and in the reversed bias, then this circuit is cut off, and we have V out is following same as V in. V out is equal to V in. Again, we have the same problem here. This resistance in this condition, just keep in mind that this resistance R and this V out here, this resistance R is expected to be much smaller than the load resistor that we will be connecting here. If you want to plot this curve, let's say this is our input voltage. When V in is less than VR, this is our VR, and our input voltage is less than VR, means is here or here. In these conditions, V out is VR. That means we have this. This is what we have when V in is less than VR. When V in is greater than VR, this is our VR, and it is greater than VR, then our output voltage follows the input voltage. like this. So the output voltage, the negative end of the output voltage gets clipped, and we can choose this VR to be somewhere anywhere along this from here to here or here. You should notice that if VR is somewhere higher than this, then all the voltage will be clipped out, and if this is something like lower than this certain voltage, then there will be no clipping at all. And one final variation of this circuit could be if we reverse this diode D, and you will notice that we will analyze this last part also very quickly. Again, but depending upon so let's say V in is greater than VR. If V in is greater than VR, then this diode is forward biased, and when this diode is forward biased, this output voltage will be following the input voltage. V out will be equal to V in. This is the condition. This is the condition of V input is greater than VR. And when V in is less than, and I will write D is on. And when then V in is less than VR, this diode is reverse bias, and D is off here, and then V out will be equal to VR. When the diode is off, the V out voltage will be the same as V in. Of course, there will be IR drop, and we assume that the drop in this R is very less, and that is possible only when your output load resistance is much higher than this this resistor R in series. And if you try to plot this graph, when V in is greater than VR, V out is V in. We have this curve. And when V in is less than VR, this curve. So this is how the diode clipping simple circuits look like. So let's move on to look into some more details into the diode clipping circuit that we saw. And in this moving forward, we'll look into the transfer characteristics or the variation of this output voltage V0 with respect to the input voltage V in. We'll no more treat this diode D as an ideal diode. It's a real diode, and we'll model it in a way that there is a drop across this diode, which is V gamma. We'll call it V gamma, which is typically like a 0.7 volt in any silicon diode, and we will assume that it has some resistance in the forward bias. We will call it RF, or the forward bias resistance of this diode. Now, when we assume these two things, our method is going to be still the same. We will consider at what input voltage this diode D is going to be forward biased, and in what what ranges is going to be reverse biased. If you look closely, then this end of this diode is going to be at least VR plus V gamma to be in the forward bias. So let's write this equation that when V in is greater than VR plus V gamma, in that case the diode D is on. And when that happens, this whole circuit is going to be replaced by an equivalent circuit which will look like this. This diode is going to be replaced by a resistor and a drop across this diode, and then this VR voltage, and like this. So this is resistor R, this is V gamma, this is VR, and we are trying to find out the output voltage V out across this when this voltage is V in, which is greater than VR plus V gamma. This is our circuit, simplified circuit. To do this, we use the Kirchhoff law. Let's assume that there is a current I flowing in this loop, and this current I will be given by this voltage V in minus these two voltages, sum of these voltages. I write V in minus V gamma plus VR divided by the total resistors R plus, we call it RF, R plus RF. And now our aim is to find out the output voltage and see how it varies with respect to V in. So we can find out V out by subtracting this IR drop here from this V in, and we get V out is equal to V in minus I into R, and V in, I is this one, V in minus Vy V gamma plus VR divided by R plus RF multiplied by the resistance R here. And let's simplify this here. V in into R minus V in into R cancels. So we have V in into RF, V in into RF divided by R plus RF. And from here, let's see the simplification here. V in into R was cancelled, so we have minus, minus, this becomes plus. And this VR had got cancelled, so divided by R plus RF multiplied by. Now this whole thing stays there. V gamma plus VR. You have an opportunity to verify it, but let's do it once more. V in into R, V in into R, and V in into R. So this term cancels. And we have V in into RF divided by R plus RF, this term. And then plus R divided by R plus RF. And this is minus, minus, plus V gamma plus VR. So this is the expression of, we will reverse this thing and write it as RF multiplied by V in. What it does is, we write this equation V out in terms of V in and some constant. So we have a slope of x and y axis. We will plot this third thing, but let's consider the other case first. When V in is less than this, the sum of this voltage required to bias this. So when V in is less than VR plus V gamma, VR plus V gamma is this voltage across this plus this forward bias voltage of this. In that case, the diode D is going to be off. We write diode D is off. And when that happens, the circuit looks like this. This is V out and this is V in. And in that case, the output voltage simply follows the V in. And in that case, V out is equal to V in. Now with these things in place, we can now try to plot the transfer characteristics of this curve. I am going to, okay, so let's look at this curve here, which I plotted like this. And this is the input voltage, we call it V in, and this is our output voltage, V out, on the y-axis. So let's take this simpler fast first. When V in is less than VR plus Vy, let's say VR plus Vy is marked somewhere here. The output voltage simply follows the input voltage. It has a slope of unity, so it's making this line is making a 45 degree with the x-axis, which is V in. And when this becomes more than this VR plus Vy, we have this equation. And in this equation, we have, this is the slope of our curve. Now RF is very, very small compared to R. So Rn, and that's the one reason we have included the R in this whole circuit. And therefore, this slope is going to be very, very gentle slope. This line, it has a slope of RF divided by R plus RF. So this is our circuit, this transfer characteristics look like. We can verify this equation by substituting in place of V in. If we substitute this value, we should get the same value, which, because this is the junction of these two slopes, we should get this output value as VR plus Vy. So let's do that, make sure our equation is correct before we proceed further. So when I come here, when V in is equal to VR plus V gamma, we have V out as equal to RF multiplied by, instead of V in, I am writing VR plus V gamma plus R multiplied by this VR plus V gamma divided by R plus RF. We have RF here. Now if you take this VR plus V gamma common from there, inside the bracket we have RF plus R, and RF plus R cancels with RF plus R, so we get VR plus V gamma, and which shows that our equation is correct, just to make sure our calculations are not something wrong. With this transfer characteristics in place, we can proceed to plot a how does the output graph varies with respect to a given input curve. But before we do that, we want to mention that, let's say this RF is 0. What happens to this equation when RF is equal to 0? So in this case, if RF is equal to 0, then V out becomes equal to, this thing is 0, this thing is 0, so this becomes R divided by R multiplied by V gamma plus VR, or this becomes VR plus V gamma. What does that mean? That our output voltage will then become constant at VR plus V gamma. So this whole thing will look like this. In case there is, we assume the diode to have a forward resistance of 0. So this will be required in our next, when we plot this graph next. And so let's try to do this. And in this curve, what we are trying to do is, we are trying to give an input voltage, this whole thing, and trying to do an output, plot the output graph. So I'm going to remove the circuit here, and we have an input graph that, let's say, varies like this. So this is our input sinusoidal waveform, and this is our output sinusoidal, and we are trying to plot an output sinusoidal, or see how the output graph looks like. You can plot it here if you need to. So when the input is 0, the output is 0. So we start it from here, and as the input increases, the output also increases in the same fashion, because for every Vi, we have an output Vi. So this graph looks like this. And it happens till here. And let's say if RF were 0, this graph would have been flat. But because of the fact that this has a little tapering here, the output is not flat in this duration. And instead of that, it looks something like a little bulging curve. And that happens because of this slope. The peak of this slope matches with the point here. And then finally, when the voltage group drops below this, the output voltage is again following the same input voltage. So our graph looks like this. And this is our input curve. So this is how the precise shape of the curve of this diode clipping circuit. So I hope you can analyze this, find out what the peak values of these voltage curves are,
and it takes into account and how you can analyze this circuit with those given assumption. Few things you need to keep in mind. If you take this diode to be ideal and you could possibly remove V gamma, then this, and then you could possibly simplify this more by making this slope look like this and things like that. In the very beginning that we have taken, and our output voltage simply goes like this and flat like this, and this voltage will be VR instead of VR plus V gamma. But this whole analysis takes into account a more detailed insight of the diode as well. Thanks for taking a look.